Now let us try to solve this problem. The problem statement is silicon dioxide powder, actually this is also called silica. Okay, it's the silica powder. Silicon dioxide powder, its flow rate has been given, which is moist with 50 kg per hour of 4 weight percent ethanol solution. So 4 weight percent ethanol solution means 4 weight percent of ethanol will be there in aqueous solution. So out of 50 kg, 4% of 50 kg will be 2 kg, right? So it will be 2 kg of ethanol and 48 kg of water. Okay, has to be washed in a washer using 1000 kg per hour of water. So this water is the washing liquid. Okay, so this is the entrained liquid and this is the washing liquid. All inputs are at 25 degrees centigrade and 1 atmosphere pressure. So input conditions are given, and remember we have not talked about any PSD. So particle size distribution is not a criteria over here and it has not been mentioned. So we have to choose the stream class accordingly. So there are 3 problems that we have to solve. The first problem is simulate a single stage solid washer. So in this case we have to use S wash block in adiabatic manner such that the washed solid stream contains 10 weight percent of the liquid. So the outlet condition of the solid stream has been specified over here, and from there you have to calculate the liquid to solid mass ratio. And in the second problem they are asking you to provide the heat duty. So this is the outlet flash condition has to be mentioned over here, that's what they say, and 90% of mixing efficiency. So here it is not 100% efficiency. In the first problem nothing has been talked about mixing efficiency, so we can always consider it to be 1 or 100%. In the second case we have to use 90% mixing efficiency, and we will see the change in the result that we have to check. In the third problem we have to repeat this exercise with a 3-stage washer. That means we have to use a CCD block and compare the result. So this is the total problem that we have to solve. Now let us go back to Aspen Plus. So for that we have to first go to the properties and we have to add in the relevant components. So first it is a silicon dioxide. So this is the solid product that we have, silicon dioxide. Then we have 4 weight percent of ethanol, that is our entrained liquid. So we have to add ethanol and water. So these 3 things we have, and do not forget it should be solid. We are dealing with solid SiO2, and then press next. Obviously we have to use solids, and remember we are using ethanol and water system, so we cannot avoid any vapor liquid equilibria in this case. We have 2 different chemicals that may interact, so we have to use a suitable property method for that. So let us use NRTL. Okay, so we will use NRTL also. So we have selected two different property methods to work with. So in the binary parameter, it will ask for the binary parameter. Now run. Now we have results available with warning. So let us see what kind of warning it is. So it says, warning in physical property system parameter RKTZRA element 1. I'm not sure what this RKTZRA means. We have to check. So lower bound violated for component SiO2. So some RKTZRA that is being violated. Now let us check what is this RKTZRA before we go forward. For that, we have to check the Aspen help file to know it better. So we go to Aspen help, and here it is RKTZRA, right? So it is liquid molar volume. It is liquid molar volume. So it says it is racket equation parameter RKTZRA for the general pure component liquid molar volume. Now think of the situation that we are dealing with SiO2 solid, right? We are dealing with the SiO2 solid. Now we do not have any liquid form of SiO2. Anyway, the melting point of silica is somewhat around 1700 degrees centigrade, and we are working at 25 degrees centigrade. So no way we are near to liquid form of silica. So this liquid molar volume, even if there is a parametrical violation for SiO2, it really doesn't bother us. At least for this problem, this is not a botheration for us. So we can just ignore this warning. Okay. So let us go to the simulation window. For the time being, let us delete this CCD. And we have to set the liquid input. Now liquid input, it is 25 degrees centigrade and 1 atmosphere pressure, isn't it? Let us check it. Yeah, all inputs are at 25 degrees centigrade and 1 atmosphere pressure. So that's exactly what we are doing. So 25 degrees centigrade and 1 atmosphere pressure. And what is the liquid flow rate? The feed rate is 1000 kg per hour of water. So this is mass flow. Water is 1000 kg per hour. And then solid again, here it is 25 and 1 atmosphere. And we have in mixed, we have 50 kg of, so it is moist with 50 kg per hour of 4 weight % ethanol solution, right? So we have solution 50 kg per hour in which mass fraction of ethanol is 0.04, that is 4%, and water will be 0.96, that is 96%. total it will be 100%. And we have to add the solid SiO2, and we have done a mistake over here because we have forgotten to set the stream properly. So in this case, we have to fix the solid stream first. So you go back to the setup, and here stream class, and put remember, we do not have any particle size distribution over here, so we choose mix ClSLD. It says with substreams mixed Cl solid, use when you have conventional solids present but no particle size distribution. So we do not have any particle size distribution, so we will use mix ClSLD. Okay. The moment we choose it, then this ClSLD is open for us, where we can add in the value of solid SiO2. So this is 25 degrees centigrade, 1 atmosphere pressure, and mass flow rate of how much? It is 500 kg per hour. So this is 500 kg per hour. Okay. So this has been fixed, both the inputs. Now let us open the block. Now let us put the liquid and solid mass ratio. Now this liquid to solid mass ratio we have to calculate, because what information do we have? We have this information that washed solid stream contains 10 weight% of the liquid. Okay. Now suppose we have X amount of liquid. That means X by 500 plus X, because it is the solid amount. So X by 500 plus X will be 10%. Right? So you just calculate it. So it will be X is equal to 50 plus 0.1X. That means 0.9 of X is equal to 50. And that will be, so your X is equal to 50 by 0.9. Right? Then what is the liquid to solid mass ratio? It will be X by 500. That means it will be 50 by 0.9 into 500. So this will be 10. So 1 by 9. Okay. So 1 by 9 will be 0.11, something like this. Okay. So we have to use this figure as liquid to mass ratio. Right? So let us go back to our Aspen plus simulation window. So we have to write it 0.11111. Okay. And mixing efficiency is 100%. That is one. And we run the system in adiabatic manner. So we do not give any extra information in the system. We let it run by its own. Okay. So it will calculate the flash conditions by itself. In other words, the problem is defined properly. Now it is ready to run. So let us run. Yeah. Now go to the result summary stream. Now first thing that you have to check, what is the outlet stream. Now it is, obviously it is operating at 1 atmosphere pressure. The pressure has not been changed, but the temperature is slightly changed because it is an adiabatic system. So in the flash condition, output has been calculated as 25.002. Okay, although the temperature changed, very minimum, somewhat it has changed. Okay, so this information is there. And what about the mass flow? Okay, check the mass flow. Now here you see in the solid stream you had 500 kg of silica, 2 kg of ethanol, and water was 48 kg, right? Now what is after washing? S out. This is 500, and what is the liquid to solid mass ratio over here? The total mass is 555.556, and here the solid is 500. So what is the liquid to solid? Liquid is this one minus 500. So it will be 55.556 by 500. So this, if you calculate, you will get 0.11. So that is the liquid to solid mass ratio that you have got. Now let us calculate the mixing efficiency and see whether it is 100% efficient. For that, so what is our mixing efficiency? It is, if you remember, it is X in S minus X out S by X in S minus X out L. So what is Xi in S? It will be 2 by 50. It is 2 by 50 because it is 48%, right? So the mass fraction of dissolved component in the liquid is 2 by 50. It is 48%. And what is the mass fraction of dissolved component in the liquid which is coming along with the solid stream? That should be X out S. That will be 0.10582 by, what is the liquid quantity? It will be 55.556. Right? So that is the liquid quantity, out of which 0.10582 is the dissolved component. And what is X out L? This will be here, ethanol. It will be 1.89418 by total amount of liquid. That is 994.444. Okay. So let us calculate this. So for that, let us go to the MATLAB window. So we will write it, say we'll write x1 is equal to, it is 2 by 50, x2 is equal to 0.10582 by 55.5556, and say y2 will be 1.89418 by 994.444, and the efficiency will be x1 minus x2 by x1 minus Y2. So this is our efficiency. Let us calculate. It will be 100% efficiency. Okay. Now, let us change the problem, the second problem, which says we have to use 10 kilowatt duty and 90% mixing efficiency. So in our second problem, we will use the outlet flash condition. The pressure is unchanged. Nothing has been talked about pressure. So let the pressure be 1 atmosphere itself. And we have to give the heat duty. So heat duty is 10 kilowatt. So provide 10 kilowatt heat duty. And specification, the mixing efficiency, it is 90%, right? So just put 0.9 over here. Okay. And run the system once again. Yeah. So it has run very fast. Go back to the result summary. First, let us check the temperature. So here you see the pressure remains unchanged throughout, but the outlet temperature has increased. Earlier, you remember, we found 25.002 degrees centigrade. Hardly there was any increase in temperature. But in this case, we are getting a higher temperature. So it from 25 degrees centigrade to 32.65 degrees centigrade. So this increase in temperature is due to the 10 kilowatt heat duty that we are giving. Okay, so that is the reason we are getting higher temperature. And you come down and see the mass flow. Here you see 90% efficiency. Here you had 0.10582. So in the outlet of solid stream you had 0.10582, but in this case you are getting 0.30, so it has increased. So amount of ethanol has increased in the solid outlet. So that is evident, right? Because you have decreased the efficiency. So the washer is not efficient enough in removing the dissolved component. Okay. So now let us calculate this dissolved component once again. So it will be XIN will be 2 by 50 as before, but S out, this will be this fraction by 55.556, and here it will be this by this. So let us see what is the mixing efficiency. So for that, let us bring the MATLAB window once again. So here in this case it will be 0.307329. 307329, and Y2 will be 1.69267. 69267. Okay. So we have redefined x1, x2 and y2, and then find out the efficiency, mixing efficiency. You get 0.9. Okay. So that's how the liquid to mass ratio and mixing efficiency has to be set for a single stage washer. Now go back to the example problem, and we have our third problem left, which is to repeat this exercise with 3-stage washer, okay, and compare the result. Anyway, so let us go and check the 3-stage washer. For that, we have to add in the CCD block. So let us take the CCD block over here, and we will input the same S in and L in. So we have to use a couple of manipulators over here. So one manipulator we'll put over here and another manipulator over here. Okay, so now this scene will reconnect destination with this one. Alien also will reconnect destination to this duplicator, and from this duplicator, or the output will be at this point, and yes, so these are connected, and this liquid also will be connected to liquid bottom, and another material stream from here, duplicator, will come to this solid input, and then material stream out. So this is the liquid out, and this is solid out. Now let us change the name. Say this one is L1 out. Let us name it L1 out and rename it as S1 out. Okay, so liquid 1 out and solid 1 out. This one, let us rename it as liquid 2 out, and this one will be solid 2 out. Okay, and this one rename it as washer 1. This one B2 rename it as washer 2. Okay, so now everything is set, all the inputs are defined, only the washer has to be set. So washer input, number of stages, 3 stages. So we have 3 stages. Now here the flash condition is mandatory. Remember, the flash condition is mandatory over here. So let us put the flash condition, the temperature and pressure, none of them are changed. And the stage, let us give only one efficiency, that is mixing efficiency. And liquid to solid mass ratio, you remember it is 0.1111. Okay. Now let us give only one stage information. So stage 2 and stage 3, if the information is different, that means if the liquid to mass ratio is different or the mixing efficiency is different, then you can set the profile of individual stage information. But if you do not give any information about second stage or third stage or subsequent stages whatsoever, then the system will assume that all the subsequent stages will have the same data as that of the first stage. So here it is set, and you check the streams, they have automatically been set. So the S3 and S4, What is S3? If you check, S3 is the liquid in the L in the washer 2, and this one is S in the washer 2. So solid in washer 2 and liquid in washer 2. So here you see the solid in washer 2, it has been given in the top stage, right? And liquid in solid in washer 2, that will be in the bottom stage, stage number 3. And product stream, it will be reverse. The L2 out, that is the liquid out, is over stage 1, whereas S2 out is under stage 3. Okay? So that's how the stream has been automatically selected. If you have side feed stream, you remember there was a set of side feed stream that you can add. If you add them, then there will be more number of streams and you will be asked to put in the stage number. Suppose you have 10 stages and you have 2 streams. One is going into stage number 3, another is going into stage number 7. Then there will be more number of such streams that will come over here at this point. So stream number 3 will come here, stream number 4 will come here, and this stage profile will be blank. So here you have to write the stage information. Suppose the stream number 2 you have put in the stage number 3, then you have to write over stage number 3 and is stage number 7. Automatically, this will become stage number 10. If it is a 10 stages column, then it will be 10. Okay. So those extra information you have to provide. Otherwise, they are all set. And we also have to put the heat duty information over here, because otherwise we cannot compare with a single stage washer. So let us put the entire heat duty in the stage 1 itself, 10 kilowatt of heat duty that we had. Everything we put into the stage 1. Stage 2 and stage 3, we are not mentioning anything. That means there is no heat duty in those 2 stages. Now here, everything we have set it. Now let us run. Yeah. Now the results are available. Now let us go to the result summary. Check the streams. Okay, so many new streams have come up. Now we check one by one, but before that, let us set them in order. So let us write S in and S1 out, S2 out, and then L1 out and L2 out. Rest of the things are not important for us. Okay, lean also we have to write. So it is LIN, that is entry. So let us put LIN. Okay, so that is the input. Input always it is 1000 kg per hour. So it was not that important. Okay. First, let us check the temperature profile, because there is nothing to check on the pressure, because pressure is always same. Temperature, as observed previously, the S1 out, that is the outlet of single stage washer, it gave us 32.65 degrees centigrade because of 10 kilowatt heat duty. On the other hand, S2 out, you find it 25.1604. The solid outlet stream in the washer 2, it is not that heated. On the other hand, if you see L2 out, this is 33.7363. Now, why it is so? In this case, S1 out temperature and L1 out temperature are same. But in this case, S2 out temperature and L2 out temperatures are different, because there are different stages. Remember, it is a 3-stage operation. So, in the top stage, the temperature has increased because it is in stage 1. Okay, so we have given the entire 10 kilowatt of heat in stage 1 itself. So the temperature of L2 out has rise to 33.7363 degrees centigrade. On the other hand, stage 2 and stage 3, they have not got much share of the heat, so their temperature is quite less. I mean, we have not checked the temperature of S2. That you can always check in the stage profile temperature. So if you see the results over here, so the profiles of washer 2, here you will find the temperature of stage 2 as well. So you can see the entire heat duty has been given in stage 1. So stage 2 and stage 3 doesn't get any heat duty. So temperature of stage 1 is 33.73 and stage 2 and 3, they have less temperature. Okay. And go back to the streams once again, because we have to check the mass flows. Yes. So here, compare the S1 out and S2 out. You see, S1 out, the mass flow rate of ethanol in single stage washer, it was 0.3 kg. So from 2 kg to 0.3 kg it has reduced. But what about S2 out? It is 0.0068 kg. So almost nothing. So with extra number of stages, you have been able to wash more and more of dissolved component out of the system. Okay. So more number of stages, washing will be better. So that's what it means. Now with 90% efficiency, you are getting this much because you have 3-stage washer. With 100% efficiency, just check for the sake of our curiosity, we can check the input of washer 2 you have to put in as 1. For a fair comparison, we can put it 1 as well, and then we run the system and check the data once again. So these are the streams. Yes. So here you can see S1 out, it is 0.10582 and S2 out it is 0.00032. Okay. So it is almost 1/100th of the quantity. So this is almost nothing is there. So we can say the S2 out, that is the solid stream output from the 3-stage washer, it is almost ethanol free. So with that, we end this lecture. I hope you have enjoyed it, and we'll come back with yet another interesting lecture soon. Thank you.